Hello all, my name is Minxiang Gong. I'm a graduate student from Georgia Institute of Technology. I joined the Integrated Circuit and System Research Laboratory advised by Professor Arijit in 2019. My researches focus on mixed signal circuits design and control for high voltage converters. Today I will introduce the review and outlook on recent topologies of non-isolated 48-to-1V DC-DC converters for data centers. This is the outline of this talk. First, I will introduce the motivation of 48-to-1V conversion. Then I will talk about topologies for high voltage converters, start from synchronous buck converter, followed by modified buck converters and hybrid converters. Then I will talk about outlooks of different topologies with simulation results and figure of merit. Finally, I will give conclusions. First is the motivation. This figure shows the current and future power distributions in data centers. First, they both have an AC to DC power converter as the front end to generate a 48V DC power bus. The difference appears on the server rack. In the current system, it uses two-stage solution and a 12 intermediate power bus. The efficiency is limited by the two-stage cascaded conversion and high loss on 12V power bus. In the future system, the 48V input is directly connected to the package of the processor, and the converter inside it converts 48-to-1V. By doing this, it reduces losses on the motherboard and the power bus, and also reduces system volume significantly. Therefore, a package-integrated 48-to-1V converter is highly desirable. This slide shows several requirements of the above high-voltage converter that determine our design space. First, we need high efficiency, of course. Therefore, we want to have a direct down conversion instead of multi-stage. High-performance switches such as gallium nitride are also desirable at the sacrifice of monolithic integration. Second, the converter should be small enough so that it can be integrated in the package with the processor. So isolated topology is not suitable. Moreover, we should use frequency scaling to reduce size of passive components. Third, since the converter is located adjacent to the processor, it should have good dynamic behavior to provide tight regulation of the output. Therefore, inductor at the output is preferable. In conclusion, these requirements lead us to the non-isolated, heterogeneous integrated, high-frequency, switching inductor, direct down conversion topology. Now I will talk about synchronous buck converter. Synchronous buck converter has been the most popular topology in a long time. As shown in the figure, it consists of a high-side switch, a low-side switch with an inductor and a capacitor at the output. It has two operating states that charge and discharge the inductor, respectively. The corresponding steady-state waveform is shown on the right. In the state 1, high-side switch is closed and the inductor is charged by VE. The inductor current ramps up. In the second state, low-side switch is closed and the inductor is discharged. The inductor current decreases. By repeating this, the inductor delivers current to the output. The pulse voltage VSW on the inductor switching node is averaged by the LC filter, and it becomes the output voltage. Therefore, the output is the pulse width modulated voltage, which is determined by the duty ratio, T1 over T, or on time of high-side switch over the entire period. We can change the on time to regulate the output. This figure shows major losses in a synchronous buck converter. The losses can be divided into conduction and switching losses. Conduction losses come from resistance of switches and current ripple on the inductors. Switching losses are more important in our consideration. First, in each cycle, the switching node capacitor is charged to the switching voltage, delta VSW, which is V in here. Second, there exists non-zero voltage and current during the transition time of the switch that leads to cross-current losses. It is also called hard switching. The above two losses both scale with the frequency and switching voltage. Therefore, in high voltage, high frequency converter, these losses are significant. This figure shows the simulated total losses and high side on time over input voltage of synchronous buck converter under certain condition. Although we keep same frequency, output voltage, and current, the total losses increase 3.5 times. On the other hand, the high side on time decreases to several nanoseconds. Such short on time not only limits control headroom, but also prevents us to further shrink the system volume. These two limitations of synchronous buck converter reveal major challenges in high voltage converter designs. Since they both scale with the switching voltage, techniques to reduce switching voltage become the key point in high voltage converters. Next, I will talk about modified buck converter. A lot of efforts have been done to improve conventional buck converters. A good example is the series capacitor buck converter. It adds one capacitor to a two-phase synchronous buck converter. This capacitor is used to block the inductor from the input voltage. Thus, it can lower the switching voltage. The following slides describe operating states of a series capacitor buck converter. At state 1, L1 is charged by capacitor C-fly instead of Vin, and L2 is discharged. The voltage on switching node VSW1 is half of Vin, and the voltage on the capacitor is increased. In the state 2, L1 and L2 are both discharged. Their currents are decreasing. In state 3, L1 is discharged, and L2 is charged by C-fly. The switching voltage VSW2 is half of Vin, and the capacitor voltage is decreasing. The next state is same with state 2. Both the inductors are discharged. This is the whole operating cycle of a series capacitor buck converter. We can see the switching voltage is reduced by half. Therefore, switching losses are reduced as well as voltage stress on switches. Moreover, since the output is the average of switching node voltage, the on time of state 1 and state 3 is extended 2 times. In conclusion, series capacitor buck converter effectively improves the efficiency and extends the on time with low area and control overhead. Therefore, we can make two considerations. First, since it can be embedded in charging and discharging paths of flying capacitors, multi-phase interleaving operation is desired. It can support higher output current and reduce the current and voltage ripple. Second, switching capacitor methods can be used to effectively bring down the switching voltage. Therefore, we can think about using more capacitors to bring down the switching voltage many times. Thus, the topology has features of both switching capacitor and switching inductor, that it becomes a hybrid topology. Now I will talk about hybrid converters. Before we look at topologies, I will introduce the concept of soft charging. In the first scenario, C2 is charged by C1. When the switch closes, since capacitor voltage cannot change instantaneously, the mismatch of the initial capacitor voltages, VC1 and VC2, will be present across the switch resistor, resulting in a large instantaneous current and cause charge redistribution loss. This is the capacitor hard charging, that a capacitor is charged by another capacitor, or voltage loss. In the second scenario, there is an inductor between capacitors. When switch turns on, since the inductor voltage can change instantaneously, there is no voltage mismatch across the switch resistance. With this technique, the capacitor charging loss is recovered through the inductor. This is the capacitor soft charging, that a capacitor is charged by an inductor or a current load. To achieve soft charging of a switched capacitor converter, A simple way is to add an inductor at the output. This is consistent with the design space above, that we want an inductor at the output. However, if we keep the original switched capacitor operating state, the voltage on the inductor is maintained around 1/4 VA. We still get the fixed conversion ratio. We can add another inductor freewheeling state to discharge the inductor, and it doesn't require any additional component. By doing this, we can get a pulse-width modulated output. However, this topology has another issue. Two switches are in series when discharging the inductor. That increases the conduction loss. This leads to another modification. As discussed above, multi-phase operation is preferred. Therefore, another inductor is added to previous topology. Now it has the desired two-phase operation, and it also removes two switches from the previous topology to get a single switch path. Next, I will show operating states of it. In state 1, L1 is charged by flying capacitors C-fly1 and C-fly3, and L2 is discharged. The voltage on VSW1 is 1/4 Vin since the capacitor blocks the input voltage. In state 2, both inductors are discharged, and there is no current through capacitors. In state 3, L1 is discharged, and L2 is charged by C-fly2 and C-fly3, and the voltage on VSW2 is 1/4 Vin. The next state is same with state 2. This is the entire operating state. It is similar with series capacitor buck converter, but it has more flying capacitors. Therefore, the switching voltage is reduced to 1/4 Vin, and on time of state 1 and 3 is extended to 4 times. It greatly improves the efficiency with low system complexity. It also takes the benefit of the high switch utilization of a Dickson converter. However, in state 1 and 3, if voltages on C-fly1 and C-fly3 are not equal, hard charging still appears when these two capacitors are connected. One solution is to split this state into two, as shown on the right. At first, C-fly3 is discharged by the inductor. When voltage on C-fly3 is reduced and equal to C-fly1, two capacitors are connected. Thus, it avoids hard charging, but increases the control complexity. To address the above issue, two more inductors are added to provide soft charging between flying capacitors. Now, each capacitor is connected to an inductor. As shown on the right, in state 1 and 3, all capacitors are charged by inductors. There is no capacitors connected directly. Thus, it achieves soft charging without split phase control or capacitor sizing strategy. We have discussed about hybrid converters based on Dickson converters. Other switched capacitor topology are also suitable for hybrid converters. Now I introduce another kind of hybrid topology. From above discussion, SC converters can bring down the voltage efficiently, while a buck converter is good at regulating the output. It is proposed in reference 10 that the buck converter can serve as a current load between capacitors to achieve soft charging. As shown in the figure, both the switched capacitor stage and the buck stage are working in the desired condition. The buck stage is operating at a much higher frequency, so the intermediate voltage Vm is no longer restricted to small voltage ripple. The energy stored on capacitors can be efficiently used. This figure shows another type of merged two-stage topology. Series capacitor buck converter is used as the second stage, so it achieves two-phase operation and has multiplication effect of voltage bring down, 4 times switching voltage reduction with two capacitors. Now I will talk about simulation results and figure of merit. This figure shows spice simulation of different topologies. Compared to synchronous buck converter, modified buck converters show good improvement. Hybrid converters show around 10% improvement of peak efficiency. Moreover, hybrid converters have relaxed on-time that is capable for high-frequency operation. This slide shows a figure of merit. It consists of frequency, input voltage, and conversion ratio. Each of them is related to design parameters. Higher form reveals challenges of efficiency and implementation. This figure shows recent state-of-the-art on high-voltage converters. We can see that the efficiency of buck topologies, which are blue points, is reduced dramatically as form increases. This blue region shows our estimated buck limitation. Because of the on-time limitation, the highest frequency of a 48-to-1V synchronous buck converter is around 5 MHz, and the peak efficiency is also restricted below 80%. The yellow region shows current works on hybrid converters. Current works are in low frequency range, so their forms are low. However, with our simulation results, we estimate that hybrid topologies can achieve near 90% peak efficiency as form increases. It shows great superiorities over buck topology. Now I will give conclusion. First, synchronous buck converter is well developed, but its frequency and conversion ratio are limited. Margins for further improvement are small. Second, hybrid converters show promising results. High-frequency operation, dynamic behavior, and integration of hybrid converters need intense research in the future. At last, topology is one of the key enabling techniques of efficient power delivery, but other techniques such as power switches, controls, and integration are also important. These are references. This is the acknowledgement. Thank you for listening.